Okay, so for the next 4 days, things really build on each other. Okay? What we do today affects our lesson tomorrow, affects our lesson Thursday, which will also affect our lesson Friday. Okay? It's not bad. It's actually nice because what we do today, you get to practice again tomorrow, and you get to practice again Thursday. Okay? We're going to do lots of repeating. Okay? It's not to scare you. It's actually a good thing because we get to keep doing it over and over. Okay? So I want to go back to this concept of increasing and decreasing. Do you agree that if I say we have, three things can happen in our graph. We can increase, we can decrease, or we can stay the same. Right? There's really nothing else that can happen. Okay? Increase, decrease, or stay the same. If we are increasing, what's happening with our y values? They're getting bigger. Okay? If we're decreasing, what's happening with our y values? They're getting smaller. And if we're constant, your y values are staying the same. I know that seems very elementary, but I just want you to get a mental picture. And we'll draw some pictures too. Okay? Increasing, decreasing, or constant are our three options in any graph. Okay? And what we are going to be able to do is using our calculus and our knowledge of slope, we will identify where a graph is increasing, decreasing, and constant based on the derivative, whether it be a derivative graph or a derivative like with the algebra. Okay? We don't necessarily need the function graph to determine where these things are happening. Okay? I should probably get my notes out so I know. Okay. So if we have an increasing piece like this, what's true about all of the slopes? All of the slopes are positive, right? If we drew little itty bitty tangent lines, they would all have positive slopes, which means our derivative is positive. So if we have an increasing piece, we know the derivative is positive. Can we all agree on that? Okay. So maybe you wrote anything about increasing, maybe making a note that f prime of x is greater than 0 might be a good thing to remember. Okay. Here's a little piece where f is decreasing. What's true about all of those slopes? We have negative slopes. All of these tangent lines that we would draw would have negative slopes. Well, our derivative means slope of the tangent line. So if we have a decreasing piece, our derivative will be less than 0. Okay, our derivative is going to be negative if we are decreasing. Okay? And I know we've talked about this before, but I really want to hammer it in before we get to the other stuff, okay? If our function is constant, what's the slope? 0. Okay? So we know what it looks like. Now we know what it means based on the derivative. Okay? What we are going to do is we are going to take a function, okay, and we are going to figure out with a derivative where it is increasing and decreasing, okay? Don't write this down. Let's just talk about this function, okay? If I were to give you, if we were to write an increasing interval, what interval would we write? -3 to 1. Okay? Everyone together. Where are we decreasing? Everybody. Where are we constant? Okay. We are increasing from -3 to 1. We are constant from 1 to 3. And we are decreasing from 3 to 5. Remember how we notate these with intervals in that open notation. Okay? Now, what if we don't have a graph? I mean, that was easy, right? We didn't need calculus for that. Okay, well, what if we don't have a graph? This is what you are going to do. Okay? Some of you really like having steps. I'm trying to help those of you who like steps. Yesterday we talked about where we could potentially have minimums or maximums. And minimums and maximums occur when we change directions. Probably important for increasing and decreasing intervals. What were those numbers that we found yesterday that could be minimums and maximums? Okay, your first job, find your critical points. Or your critical numbers. Okay, I kind of interchange points, numbers. Okay, so those critical points are going to potentially break up where we have increasing and decreasing. Notice how it said potentially. Doesn't necessarily mean it has to. But what we're going to do is we're going to draw a number line, and we're going to put our critical points on a number line. With the intervals that you have now broken up, I need you to actually test values to determine if that interval is positive or negative. And we're testing values based on, that is F prime. The font wasn't a good choice. We're testing values of F prime because F prime tells us if we're increasing or decreasing. And then you're going to read your graph, read your number line, and actually tell me the intervals. Okay, if you have a positive, then you have an increasing interval. If there's a negative, you have a decreasing interval. What? You know, some of us are like, let's check. Somebody was like creeping by when you saw it. I was peeking in. Okay. All right. This is all we're doing today. We're going to do this, is it 3 times? We're going to 1, 2, like 3.5 times. Okay? We have 3 official examples, and then I'm going to throw something else in there. Okay? So, our first official example, I want to determine where this is increasing and decreasing. Okay, we're going to start out with a nice, gentle polynomial. You see a polynomial and you say, yes, because the algebra is going to be probably fairly simple. Yes. Okay. How do we find critical numbers? Set the derivative equal to 0. Okay? So if you need to go back up to your list and remind yourself, set derivative equal to 0 and undefined for critical numbers, you may need to do that. I don't know. But we need our derivative. So our derivative is 3x squared minus 12. And in order to determine where our critical numbers are, we need to set this derivative equal to 0. Okay, do you agree that our critical numbers are at plus and minus 2? Okay. So we are going to put these numbers on a number line. Okay? And to help remind yourself what this number line represents. It is a number line of our derivative. Okay. And our critical numbers were -2 and +2. And we need to determine where our derivative is positive versus negative. Okay? So all we have to do is plug in numbers. Okay? What is a number to the left of -2?
-3.
-3. Does it matter what you choose? Just do something that is easier than another. Okay? So -3, and if we come back here to our derivative, 3 times -3 squared minus 12. What kind of number would you get? You would get positive. I don't really care what it is. I just want to know if it's bigger than 0 or less than 0. So if we have 3 times 9 minus 12, we're going to get a positive number. What's a nice number between -2 and +2? 0. Great choice. And if we plug 0 in for our derivative, we get -12. Okay? We get negative numbers. Okay? And it doesn't matter what you plug in along the interval, they're all going to be negative. Okay? If we chose 1, -1. Okay? To the right of 2. 3. 3 times 3 squared minus 12 would give us a positive number. Okay? At this point, we only have to read our number line. Okay? Where our derivative is positive means we have increasing intervals for our function. And where our derivative is negative means our function is decreasing. So we can determine that our function is decreasing from -2 to 2, and our function is increasing from -infinity to -2 and 2 to infinity. What do you think? Isn't it nice to like do something with the derivative? Like moving forward with the derivative. Okay. Now I did warn you this was a nice, gentle polynomial, right? The other two examples might not be as nice with their derivatives, or the derivatives might not be so bad, but maybe setting them equal to 0 we kind of need to talk about, or the algebra to simplify. Okay, we didn't really practice that in Unit 2. We do have to worry about the algebra to simplify now. Okay, so let's go ahead and look at two examples that are not polynomial. I'm just kidding. This one isn't that scary. Okay. Take a few seconds and determine what the derivative is for me. Okay. Our derivative. Julia, what is it?
2/3 x squared minus 9 to the exponent of -1/3 times 2x.
Do you agree? Good. Okay. Now, knowing that we need to set this equal to 0 and determine potentially where it's undefined, let's rewrite it and make it look a little different. Okay? As I said yesterday, if you have a negative exponent, I encourage you to move it across the fraction bar. So I would like to write this as 4x divided by 3 And then the x squared minus 9 to the 1/3 power would move to the denominator so that the exponent can now be positive. Okay? Why is this important? Well, we need to know where our derivative is 0 and undefined. And having that negative exponent now in the denominator as positive, it makes it easier for us to determine those undefined values. Okay? So our critical numbers. Where is our derivative equal to 0 at? If we set the numerator equal to 0, we would get 0, right? 4x equals 0 means x is 0. Okay. Our derivative is undefined wherever our denominator is 0 for the derivative. When does that happen? Plus or minus 3. Okay. If we set the denominator equal to 0, we would get x squared minus 9 equals 0. X squared equals 9. So x is plus or minus 3. That 3 in the front's not doing anything. When we cube both sides, 0 cubed is still 0. So it's really the plus or minus 3. Okay. All right. So that just means we have a few intervals to test. So if we put this on a number line, remember we are testing this on our derivative. Okay. We have 0, 3, and negative 3 to test. Work together at your pod to plug numbers into the derivative and determine the signs above each of those intervals. Yep, and that's why we label it as f prime as kind of our reminder.
So like the first one.
But it doesn't matter the actual number, it just matters the value. So here we're plugging 5. You know that 5 squared minus 9 is going to give you positive.
Wait, what did you
It wasn't
Well, 16 minus 9. Like squaring or cubing.
No, but when you like put a negative fraction, then I don't know.
Okay, so if you're cubing something, the sign is the same.
Oh no, it'd be negative
So like if you have an odd root, it's like, yeah, like the cube root of a negative 1 is still negative. Is that how? Okay. Don't get caught up in what the actual numeric value is. Just figure out if it's positive or negative.
Also negative.
Okay.
So then negative divided by negative equals positive.
How are we going? How are you plugging negative?
Because it's
Okay.
cube root.
How are the numbers? So like if you plug in a negative 2, 4 minus 4 times negative 2 is right? 4 minus 9 is negative.
Yeah,
So a negative numerator.
That's not too bad.
Yeah. Am I right?
Okay, a word of advice from your teacher. When you have a fraction, like think about what sign the numerator is, think about what sign the denominator is. Like this interval right here, if I were to plug in 1, right? If we were to plug in 1, our numerator's positive, but if I were to plug in 1, our denominator's negative. So positive over negative makes negative. What's this interval? Positive. What's this interval? Positive. What's this interval? Negative. Okay. So you would need to tell me that we are decreasing on the intervals negative infinity to negative 3 and 0 to 3. And we are increasing on the intervals negative 3 to 0 and 3 to infinity. Does anyone know what this graph looks like? It would look, isn't it nice? We can kind of get an idea of what this kind of looks like without actually knowing what it looks like because we have the increasing and decreasing intervals. We'll actually put it all together and be able to sketch it next week, but I was going to try to bring up my calculator to show you what this looks like. Now, somebody I heard make the comment, ooh, isn't it just going to alternate plus, minus, okay? And I have something for you here in a moment, okay? What is it? X squared, is it minus 9 raised to the 2/3? Decreasing, increasing, decreasing, increasing. And we determined that 3 and negative 3 were where our derivative was undefined. Interesting. There are corners there. Woo, I know, it's so cool. I love math. Okay, so what if our function was x cubed? We all know what that looks like, right? Okay, let's talk about the math behind it. Our derivative is 3x squared. What would our critical number be? Okay, if we put that on a number line, okay, our derivative is positive to the left of 0 and positive to the right of 0. Okay, it is not going to alternate every time. So just be careful with that. Now, a lot of times will it? Yeah. But especially if it's polynomial, a lot of times that will happen, but not every time. So make sure you test every interval. Also, are we increasing at 0? We kind of flatten out, right? So I would want you to tell me that this increasing interval is negative infinity to 0 and 0 to infinity. Okay. All right. Yeah, all the time in the world. All right. Last example.
Callus on my feet.
Is it harder than All right, now on the test, you see a quotient rule and you're like, man, this is nothing, okay? You guys crush the quotient rule on your test, okay? Some of you have even started doing the quotient rule, all right? We have 4x cubed times x to the 4th plus 1. Sorry. Back up. I got ahead of myself. Times x squared. Minus x to the 4th plus 1 times 2x. All over x squared squared. And on Thursday, you would have been like, done, right? Okay, but now that we're in unit 3, we are no longer done. Okay, we need to simplify this so we can determine where our derivative is 0 and undefined. Okay? So we get 4x to the fifth minus 2x to the fifth minus 2x. We have some terms we can combine. Is that what you're babbling about next?
Yeah.
Okay. So we have 2x to the fifth minus 2x over x to the fourth. Okay. Would you say that we're simplified? Not really. Okay. Factoring out the 2 in the numerator isn't necessary, but now that we're setting this equal to 0, it could become helpful. What else can we factor out of the numerator? Okay, so we can factor 2x out. Left over is x to the fourth minus 1, which means we can write our derivative as 2 times x to the fourth minus 1 all over x cubed. Okay, because this x can cancel out with one of these. Okay. All right, so our critical numbers. If our derivative is 0 and we set that numerator equal to 0. Now, some of you may really like to put all the algebra out, but we have reached a point in our mathematical careers that some algebra we can do in our head. And I feel like x to the fourth minus 1 equals 0 is something that we could do in our head. What does x equal? Okay, plus or minus 1. If you want to show me your work, you go for it. But on something like that, I am okay with you doing that in your head. X to the fourth equals 1, which means x is plus or minus 1. Okay? We also need to know where our derivative is undefined. If we set our denominator equal to 0, where is our derivative undefined? At 0. So on our number line for our derivative, we have 0, 1, and negative 1. And remember, don't get too hung up on what the actual value is. We're plugging numbers in to see if we have positive or negative intervals. All right? So this one's not so bad. We can plug in negative 2, right? Negative 2 would create a what kind of numerator? Positive. But negative 2 cubed would be negative. So we have a positive over a negative, which means this interval is negative. All right, now unfortunately we have to choose like negative 1/2 here. Okay, that's okay, we can handle it. Right? Negative 1/2 to the fourth minus 1. What kind of number is that? It is a fraction that's going to be negative, right? It's basically 1/16 minus 1. It's going to be a negative number, okay? Negative 1/2 cubed would be what kind of number? Also negative. So we would have a negative number divided by a negative number, which means we have positive values in that interval. See how I'm making my life easier by not really thinking about the number? Okay, what about positive 1/2? It would be a negative numerator over a positive denominator. And then positive over positive. Okay, so we have an increasing interval of negative 1 to 0 and 1 to infinity. We have a decreasing intervals, negative infinity to negative 1 and 0 to 1. All right, what do you think? That had a little bit more algebra than the others. Right? Okay. Let's look at your gold sheet. How many problems do you have? You have 1, 2, 3, 4, 5, 6, 7, 8, 9 problems for tonight's homework. Okay? I have an idea. Your first two problems are number 5 and number 7. How about you do number 5 and number 7 before you leave, just to make sure that we're all on the same page. Okay? Since this is the foundation for the rest of the week, let's make sure we got 5 and 7 under control.